Hello there, and welcome to the Quantum Slumber, a quiet place where curiosity gets comfortable and science takes the scenic route towards sleep. Tonight, I want to start with a simple experiment you could imagine in any laboratory, and yet it has the power to break your understanding of reality. Take two tiny particles, photons for example, and let them interact in just the right way. You entangle them, then you separate them. You send one to Tokyo and the other to New York, roughly 11,000 kilometers apart. Now here's the part your brain wants to reject. A light would need about 37 milliseconds to cross that distance. And according to Einstein's special relativity, nothing, no signal, no information can outrun light. That limit is supposed to be the universe's hard boundary. But now you measure a property of the particle in Tokyo, its polarization, its spin orientation, and in the exact moment you complete that measurement, something impossible seems to happen. The particle in New York doesn't wait, not after 37 milliseconds, not after any delay at all. Instantly, the correlations line up, stronger than anything classical physics can explain, as if distance, for a brief moment, simply doesn't matter. This is quantum entanglement, the phenomenon Einstein dismissed as spooky action at a distance. And whether you find it beautiful or unsettling, it's real, verified, repeated, unavoidable. And tonight, we're going to follow this thread carefully, not rushing, not forcing it into comfort, until it reaches somewhere that feels a little darker than physics. But first, let your shoulders drop, unclench your jaw, and take a slow breath in and out. If you enjoy these calm journeys into the strange side of reality, you can gently support the channel by liking, subscribing, and sharing a thought below. And I'd love to know where you're listening from tonight. Now, let's make the impossible feel undeniable. Entanglement sounds like a dramatic word, but at its core, it's a very specific kind of relationship. One that quantum physics allows, and classical physics simply doesn't have room for. In the everyday world, we're used to objects being separate. Two coins can be identical, two dice can be fair, two clocks can be synchronized, but each one still carries its own independent reality. If you flip one coin in Tokyo, it doesn't do anything to the coin in New York. At most, you can say they started the same. After that, each coin lives its own life. Quantum systems can refuse that separation. When two particles are prepared in an entangled state, they stop being two independent things in the way our intuition wants them to be. Instead, they become a single physical system with a shared description. Not two stories running in parallel, but one story written across two locations. And the unsettling detail is this: the shared story can remain intact even when the particles are far apart. Now, it's important to be careful with what entanglement is not, because most misunderstandings come from importing classical ideas and just turning the volume up. Entanglement is not a hidden radio signal. It's not one particle sending a message to the other the moment you measure it. There's no tiny messenger sprinting across space at infinite speed. If that were the explanation, it would collide head-on with relativity in the most obvious way. Physicists would have spotted it immediately, and the phenomenon would have collapsed into a boring engineering problem. Find the faster signal. But that's not what the data looks like. The correlations don't behave like communication. They behave like something deeper, a constraint on what outcomes can occur together. A clean way to feel this is to think in terms of a pair of gloves. If you put one glove in Tokyo and one in New York, you can open the Tokyo box and instantly know what's in New York. If Tokyo has the left glove, New York must have the right. No mystery, no spooky action. You didn't influence New York. You just learned what was already determined when you packed the boxes. For decades, many people hoped entanglement worked the same way. The particles might simply carry hidden instructions from the moment they were created, like gloves. Then measurement would just reveal what was already there. The trouble is, entanglement correlations are too strong, too structured, too mathematically particular to be explained by pre-packed instructions. At least not if you keep the basic idea that reality is local, and that nothing about a particle over there can depend on what you choose to do over here. Quantum entanglement doesn't act like two separate objects with matching labels. It acts like one object that has been distributed. Imagine you have a single chord played on a piano, one sound, one harmony. Now imagine splitting the chord across two distant rooms so that one room contains some of the notes and the other room contains the rest. If you listen to one room alone, it won't sound like the full chord. It might sound incomplete, even ambiguous. But when you compare what was heard in both rooms, the pattern locks into place. Not because one room told the other what to do, but because both were always parts of the same musical event. That's closer to the shape of entanglement. In quantum mechanics, the complete description of a system is the wave function, a mathematical object that encodes what outcomes are possible and how they relate. When particles are entangled, you can't write the wave function as particle A has its own wave function and particle B has its own wave function. You're forced to write one wave function for the pair. The system's reality is not stored inside either particle individually. It's stored in the relationship. This is why entanglement can feel like it reaches beyond space. Space tells you where things are. Entanglement tells you what they are allowed to be together. And that difference matters, because once you accept that the pair has a shared quantum state, you begin to see why measurement produces such eerie certainty. When you measure one particle, you are not merely peeking at a private property it was carrying all along. You're forcing the shared state to produce a definite outcome. The moment one side becomes definite, the other side must become compatible with it, because they were never independent to begin with. This is the point where Einstein's discomfort becomes easy to understand. He called it spooky action at a distance, and he didn't mean it as a compliment. The phrase was a warning. It was his way of saying, if quantum mechanics demands this kind of connection, then quantum mechanics must be incomplete. Something must be missing, some hidden layer that restores common sense, locality, causality, the comforting idea that distant objects are truly independent. But entanglement refuses to behave like a polite feature of nature. It behaves like a fundamental one. And here's the key. The instant knowing in entanglement is not the same thing as instant messaging. You can't use entanglement to send a message faster than light. No one in Tokyo can choose a measurement outcome and force New York to receive a specific bit of information. The outcomes are random on each side. What entanglement guarantees is the pattern of correlation when the two sides later compare results through ordinary, slower-than-light communication. That's the strange compromise nature seems to allow. On the surface, each measurement looks like chance. Spin up or spin down, horizontal or vertical. A coin toss with no obvious bias. But when the two coin tosses are compared, the pattern is too coordinated to be explained by classical chance. Not because anything traveled between them in the moment, but because the pair was never just two coins. So, by the time we reach the end of this idea, we're left with a fork that's hard to avoid. Either the universe contains non-local connections, relationships that do not respect distance the way our intuition insists they should, or our usual idea of real properties is wrong, meaning particles do not carry definite answers inside them prior to measurement in the classical sense. That is the quiet, unsettling core of entanglement. Not that it breaks physics, but that it forces physics to choose which comforting belief we're willing to surrender. For a long time, quantum entanglement lived in an uncomfortable place. It was too strange to ignore, but too slippery to pin down. You could describe it with equations. You could argue about it in papers. You could trade philosophical blows in lecture halls. But it was always tempting to believe the weirdness was only a symptom of our ignorance. That somewhere underneath the probabilistic language, the universe was still running on something more ordinary, something local, something sane. That was the hope behind a famous challenge posed in 1935, when Albert Einstein, along with Boris Podolsky and Nathan Rosen, published what became known as the EPR argument. They weren't trying to be mystical. They were trying to be precise. Their reasoning was almost painfully clean. If quantum mechanics is a complete description of reality, then it allows two distant particles to share a linked state so perfectly that by measuring one, you can immediately predict something about the other, not as a vague tendency, but with certainty. And that certainty was the problem. Because quantum mechanics also says there are pairs of properties you can't know simultaneously with perfect precision, position and momentum, for instance. The uncertainty principle isn't just a technological limitation, it's baked into the theory. A particle, in the quantum view, is not supposed to carry sharp, definite values of both at once. But EPR noticed something unsettling. With entanglement, you can choose what to measure on the particle near you, say, its position, and that choice lets you infer the position of the distant partner. If instead you choose momentum, you can infer the momentum of the distant partner. Your decision here seems to determine what kind of certainty becomes available over there. So, EPR presented the world with a fork that felt unavoidable. Either the distant particle already had those properties all along, meaning quantum mechanics is incomplete, missing some deeper variables that specify reality in advance, or your measurement here somehow reaches across space in a way that classical physics would call impossible. Einstein preferred the first option. He couldn't accept that the universe was fundamentally probabilistic. He couldn't accept that particles were undefined until someone looked. He certainly couldn't accept a world where distant objects were not truly independent. In his mind, physics had to respect two principles that felt almost sacred. Locality. Nothing that happens here can instantly influence something far away. Realism. Physical properties exist in definite form, whether or not we observe them. Quantum mechanics, taken seriously, seem to threaten both. And for a while, the debate stayed stuck in that philosophical fog, because the frustrating truth was that both sides could reproduce the same predictions for the experiments available at the time. You could argue endlessly about what quantum mechanics really means, but you couldn't force nature to answer. Then, in 1964, a physicist named John Stuart Bell did something that changed the entire landscape. Bell didn't try to settle the argument with intuition. He settled it with a theorem. He asked a deceptively simple question. If Einstein is right, if there are hidden variables that carry predetermined answers, and if nothing travels faster than light, then what limits must those predetermined answers obey? Bell showed that any theory that preserves both locality and realism must satisfy certain statistical constraints when you measure entangled particles at different detector settings. These constraints became known as Bell inequalities. They aren't opinions, they are math. If the universe is local and realistic in the way Einstein wanted, the correlations between distant measurements cannot exceed a specific ceiling, no matter how clever the hidden variables are, no matter how complicated the instructions. The ceiling is built into the logic. Quantum mechanics, however, predicts something else. It predicts correlations that climb higher than the ceiling, not infinitely higher, not by some absurd amount, but higher in a way that is small enough to miss if your experiment is sloppy, and clear enough to detect if your experiment is careful. And suddenly, the argument was no longer metaphysical. Nature could choose sides. All that was left was to build an experiment sharp enough to make the choice undeniable. That moment arrived most famously in 1982, when Ilan Aspect and his team performed a test that would become legendary. Not because it was flashy, but because it was strategically brutal. They created pairs of entangled photons and sent them to two separate detectors. Each detector could measure the photon's polarization along one of several possible settings, different angles, different questions, asked of the same particle. Here's the critical move. Aspect introduced rapid switching. The measurement settings were changed while the photons were already in flight, so quickly that, in principle, no signal traveling at the speed of light could go from one detector to the other in time to coordinate the outcomes based on the chosen settings. This matters because it kills the most comforting loophole. If the photons were secretly communicating with each other, if they were exchanging information at light speed or slower, then changing the detector settings fast enough would break the coordination. The particles wouldn't have time to agree on a story. And if the photons merely carried pre-written instructions from the moment they were created, those instructions would have to obey Bell's ceiling. But the correlations persisted. They didn't just persist. They violated Bell's inequality in exactly the way quantum mechanics predicted. The results weren't poetic. They weren't a matter of interpretation. They were statistical signatures, numbers that refused to fit inside the classical box. Aspect's experiment wasn't the end of the story either. It was the beginning of a new era. Over the decades that followed, physicists repeated and refined these tests in countless forms. Photons separated by kilometers, entangled atoms, superconducting circuits, increasingly strict designs that closed loopholes one by one, and the same pattern kept appearing. Quantum mechanics wins. The universe violates Bell's inequality. Local realism, at least as a package deal, is ruled out. It's hard to overstate what that means, because it forces a kind of philosophical surrender. You don't get to keep every comforting assumption at once. If the correlations are real, and they are, then something has to give. Either locality fails in some deep sense, meaning the universe contains connections that don't respect distance the way our everyday intuitions demand. Or realism fails, meaning particles do not carry definite properties in the classical sense prior to measurement. Or, in some way that is even more unsettling, our entire framing of what counts as separate physical objects is incomplete. That's why entanglement still feels like a bruise on common sense. Not because it's a cute paradox, not because it's a party trick for physicists, but because, when the dust settles, it leaves you holding a fact that has been verified for decades in laboratories around the world. The world is not built the way Einstein hoped, and whatever the deeper explanation turns out to be, the universe has already made one thing clear. It does not fully respect the idea that distant objects are independent, self-contained islands of reality. So after all the history, all the lab work, all the careful elimination of loopholes, you're left with a result that doesn't politely sit inside the worldview most of us grew up with. Bell's inequality is violated. The correlations are real. They're repeatable. They don't fade with distance the way any ordinary influence should. And that leaves you standing at a fork in the road, two exits that both feel wrong in a different way. One path says, the universe is non-local. Not in the cartoon sense where a particle shoots a secret message across space at impossible speed, but in a deeper sense, that what we call separation isn't the final word, that two particles can remain parts of a single physical system, even when miles or continents lie between them, that the bookkeeping of reality is not fully done in space. If that's true, then distance is not the barrier we assume it is. Space becomes less like a set of hard walls and more like a convenient map drawn over something more connected underneath. The particles aren't talking, they're not coordinating, they're simply not independent in the way classical physics trained us to expect. It's unsettling because it suggests a hidden architecture, an underlying web where separateness is, at best, incomplete. You can still keep relativity intact in the practical sense. No faster-than-light messages, no causal paradoxes you can use as a machine, but your intuition takes a hit. The universe turns out to have seams you didn't know were there. The other path says, we must abandon realism. That word sounds abstract, but the idea is painfully concrete. Realism means the particle carries definite properties: spin, polarization, position, whether or not anyone is checking. It means measurement is like opening a sealed envelope. The answer was already inside. If realism fails, then the envelope is empty until you open it. The particle does not possess a definite value in the classical sense before measurement. What exists is a spread of possibilities, superposition, not as a metaphor, but as the actual state of the system. Measurement doesn't merely reveal, it selects. It forces the world into a specific outcome from a menu of outcomes that were all, in some sense, present. And that's disturbing for a different reason. Because now, properties start to feel conditional, dependent on the act of measurement, on the context, on what question was asked. The world begins to look less like a fixed stage with objects sitting on it, and more like a set of potential answers waiting for interaction to make them definite. Neither option is comfortable. Non-locality threatens the independence of distant things. Anti-realism threatens the independence of things from observation itself. One makes the universe feel secretly connected. The other makes it feel like reality isn't fully written until it's read. And the reason this fork matters, why it feels heavier than a technical detail, is that it brushes against a boundary we normally keep protected. A boundary between physics and the inner life. Because the moment you start saying words like measurement, definite, actual, selected, you're standing uncomfortably close to questions that sound less like particles and more like experience. And that is where physics very quietly begins touching the edge of mind. Imagine you want the smallest possible experiment that still manages to offend common sense. Not a complicated machine the size of a building, not a black hole, not a thought experiment that hides behind philosophy. Just one particle of light, a single photon. You send it toward a barrier with two narrow openings, two slits, cut side by side. Behind the barrier is a screen that will register where the photon lands. If you repeat this again and again, one photon at a time, you can build up a picture of what the photon does on its way through. Now, if you were raised on the ordinary rules of the world, you already know what should happen. A thing goes through one opening or the other, like a grain of sand through a fork in a fence. If you fire a tiny bullet, it doesn't split into a ghost and take both routes. It picks a path. It passes through slit A or slit B, and then it hits the screen. So, you start the experiment the way any reasonable person would. You don't try to spy on it. You just let the photon fly, one at a time, quietly, patiently. And the first surprise is not the randomness. Random dots on the screen would be fine. A quantum particle landing unpredictably would still fit inside the idea that it took one path, but you just don't know which one. That is not what you see. As the dots accumulate, a pattern emerges, a striped pattern of bright and dark bands called an interference pattern. It's the kind of pattern you expect from waves, from ripples on a pond, from sound, from anything that can overlap with itself and either reinforce or cancel out. But this is one photon at a time. There is no second photon beside it to collide with, no crowd, no swarm, no wave made of many particles traveling together. Just one. And yet, the distribution of impacts across the screen slowly draws the signature of something that behaves like a spread-out wave passing through both slits and interfering with itself, like the photon in some sense takes both routes at once. That is already strange enough. But the experiment doesn't become famous because it's merely strange. It becomes famous because the moment you try to remove the strangeness, it punishes you. So, you decide to do the most natural thing in the world. You place a detector at the slits, something to tell you which opening the photon actually used. You're not trying to smash the photon. You can design the detector to be as gentle as physics allows. You're not trying to kick it off course. You're just asking a question. Which slit? And the instant you ask, the universe changes its behavior. The interference pattern vanishes. The stripes dissolve into a different distribution, one that looks like what you expected in the first place. The photon behaves like a particle choosing a single path, as if it went through slit A or slit B, but not both. It's hard to overstate how deep that cut goes. Because in the classical world, measurement is passive. It reveals what's already true. A thermometer doesn't create temperature. A ruler doesn't create length. A camera doesn't create a person standing in the street. But here, measurement doesn't feel like reading an answer. It feels like forcing the question to have an answer. And people naturally try to rescue intuition by saying, well, the detector must disturb the photon. That's the comforting explanation. It makes measurement ordinary again. It turns the mystery into clumsy interference. The detector bumps the photon, so the wave behavior is ruined. Except the experiment refuses to stay that simple. Because even when the interaction is engineered to be minimal, when the setup is arranged so you're not kicking the photon in any classical sense, the pattern still obeys the same rule. If which path information exists, interference dies. It doesn't matter if you personally look. It doesn't matter if anyone is watching in the human sense. What matters is whether the information is, in principle, available in the physical world, whether the universe has recorded an answer. That's where the language of quantum mechanics becomes unavoidable. Before measurement, the photon is described by a wave function, a mathematical object that assigns amplitudes, probability weights, to different possible outcomes. In the double-slit setup, that wave function spreads out. It includes both paths. The photon is not described as secretly choosing one slit while you simply lack knowledge. It is described as being in a superposition of possibilities, multiple mutually exclusive histories coexisting in the same physical description. Then measurement happens, and that superposition no longer shows up in what you observe. One outcome becomes definite. The wave function appears to collapse into a single result. The equations tell you how to predict the probabilities with stunning accuracy, but they do not hand you a satisfying story about what collapse is. Is it a literal physical process, a real event in the world? Is it just an update in knowledge? Your information changes, not reality? Do all outcomes happen and you simply find yourself in one branch of a larger multiverse? Or is there some deeper mechanism, hidden variables, that decides outcomes while still reproducing the statistics? The double slit doesn't answer those questions. It sharpens them. It forces you to admit that the word measurement is not a casual word in quantum physics. It is the place where the theory touches something we don't fully understand. The place where a soft, spread out cloud of could be turns into a hard dot of is. And once you've seen that, you start noticing how unstable the boundary feels. Because if the interference pattern disappears when information exists, then you're pushed into an uncomfortable question. What counts as information? What counts as a record? What counts as a measurement? A detector at the slit seems obvious, but what about a stray air molecule bouncing off the photon? What about thermal radiation? What about the faintest interaction with the environment? If those interactions imprint which path information into the world, even in a way no human could ever practically retrieve, does the wave behavior vanish anyway? And if so, where exactly is the dividing line between quantum possibility and classical fact? The reason this matters, why it's more than a clever lab trick, is that it reframes what you thought reality was. You start the experiment believing the photon is a little object traveling through space, doing a definite thing, and your job is simply to discover it. You end the experiment realizing that, at least at the quantum scale, doing a definite thing is not the default state of nature. The default state is a structured blur of alternatives that only resolves into a single history when the world forces it to. And that is the paradox hiding in plain sight. The more insistently you try to watch reality behave normally, the more reality behaves differently because you watched. So, when people say the double-slit experiment shows observation changes reality, they're not being poetic. They're describing a stubborn experimental fact. And once you've accepted that fact, another question starts to form, quietly, almost against your will. If measurement is not just a passive act, if it's something that participates in the production of definite outcomes, then what exactly is a measurement? And who or what gets to perform it? There's a moment in quantum physics where the mystery stops feeling like a clever laboratory trick and starts feeling like a disagreement about what the word reality even means. It's sometimes called Wigner's friend, and it begins with a simple, almost cozy setup. Picture a sealed laboratory. Inside, a scientist, Wigner's friend, runs a quantum measurement. Maybe it's the spin of an electron. Maybe it's the polarization of a photon. Something with two clean outcomes, up or down, left or right. The friend performs the measurement, looks at the detector, and writes the result down. From the friend's point of view, the story is over. A definite outcome happened. The needle pointed, the light blinked. The record exists. The measurement collapsed the uncertainty into a fact. If you asked the friend what happened, they would answer without hesitation, because for them, the universe has already made its choice. Now widen the frame. Outside the sealed lab is Wigner, an observer who has not looked inside. Wigner knows the rules of quantum mechanics, and Wigner treats the entire lab, particle, detector, friend, notebook, photons bouncing off the walls, as one physical system. And here's where the problem appears. If quantum mechanics applies to small systems, and it applies to detectors, and it applies to everything made of atoms, then, from Wigner's perspective, the lab itself should be described by a single quantum state. That state, according to the math, would be a superposition of possibilities, a branch where the friend saw spin up, wrote up, and the lab contains an up record, and a branch where the friend saw spin down, wrote down, and the lab contains a down record. In other words, the friend is sure the outcome is definite, but Wigner, if he follows the same quantum rules used everywhere else, has to describe the lab as if both outcomes still coexist. Two observers, two descriptions, both using the same physics. And you can't dismiss it as a philosophical word game, because the difference is not merely about feelings, it's about predictions. If Wigner treats the lab as a superposition, then, in principle, Wigner could perform an interference-type measurement on the entire lab system, something designed to detect whether the up and down branches still exist as a coherent quantum combination. If Wigner can do that, then the superposition wasn't truly destroyed inside the lab. It survived. But the friend will insist, no, I saw a single result. I wrote it down. The collapse already happened. So, who is right? If the friend is right, then collapse is something that happens. At the moment a conscious observer becomes aware of the outcome. If Wigner is right, then collapse is not tied to awareness, because awareness occurred inside the lab, and yet the outside description still keeps the branches alive. The discomfort is sharp because both positions feel unavoidable. If you say the friend's definite experience is the final word, you are implying that the act of observation, somewhere in the chain from particle to detector to brain, creates a fact. If you say Wigner's external quantum description is the final word, you are implying that a person can have a definite experience inside a lab that, from the outside, is still described as not yet decided. That sounds almost insulting to common sense. It sounds like telling someone, you're certain you saw a result, but from my viewpoint, you're still in a kind of quantum fog. Now, there are ways physicists respond, and each response has a price. One move is to say, quantum mechanics doesn't apply to big systems like labs and people. There's a boundary where the rules change, but then the obvious question returns. Where is that boundary exactly? At 1,000 atoms? A million? A detector? A neuron? A notebook? If the laws of physics are fundamental, it's strange to imagine they quietly stop working when the system becomes too familiar. Another move is to say, decoherence will destroy the superposition immediately. The environment will entangle with the lab so quickly that interference becomes impossible. Decoherence is real, and it explains why large-scale superpositions become effectively unobservable. But notice what it doesn't automatically do. It doesn't pick one single outcome as the one that truly happened. It explains why the branches stop talking to each other. It doesn't fully explain why you only ever live inside one branch as a single stream of experience. Another move is to embrace something like many worlds. Wigner and the friend are both right because both outcomes happen. Reality splits, and each observer inhabits a consistent branch. That preserves the math beautifully, but it asks you to accept an enormous hidden structure, a constantly branching cosmos, where collapse is only an illusion of perspective. Another move is to adopt an interpretation where collapse is objective, some physical process that happens when a system reaches a certain threshold, not human awareness, not a mystical glance, a real mechanism. That sounds appealing, but then you have to specify the mechanism. You have to show where it comes from and how it fits with everything else we know. And then there's the option that makes people quiet, maybe facts are not absolute in the way we casually assume. Maybe quantum mechanics is telling us that what is definite for one observer can remain indefinite for another until their accounts are brought together in a consistent way. Not anything goes, not chaos, but something like relational reality. Properties defined relative to an interaction, rather than floating in space as universal truths waiting to be read. If that idea makes you uneasy, it should. It means the universe may not come with a single, global ledger of outcomes written in ink. It may come with local records that become mutually locked only when systems interact. And the reason this matters for our story is that Wigner's friend doesn't just ask, when does measurement happen? It asks something sharper. If two observers can honestly apply the same physics and end up with two different states of the world, then what exactly is the thing we're calling the world? Because once you let that question breathe for a moment, you can feel the thread tightening, quietly pulling us toward the next puzzle. The kind where the problem isn't simply that reality changes when you look. It's that reality may not fully settle until different viewpoints are forced to agree on what they saw. Schrödinger came up with his famous Katinger's cat, not because he liked weird stories about pets, but because he wanted to show how quickly quantum logic becomes unbearable when you scale it up. Down at the level of electrons and photons, we have learned to tolerate the idea of superposition, a system existing in multiple possibilities at once, until a measurement forces a single outcome. It's strange, but it stays safely inside the lab. It stays small. Schrödinger's move was to ask a simple, unsettling question. If quantum rules are fundamental, why should they stop being true just because something is large enough to make you uncomfortable? So he imagined a sealed box. Inside is a cat, a tiny bit of radioactive material, a detector, and a mechanism connected to a vial of poison. The setup is designed so that if the radioactive atom decays, the detector triggers, the vial breaks, and the cat dies. If the atom does not decay, nothing happens, and the cat lives. The cruel part isn't the poison. The cruel part is the logic. Radioactive decay, in quantum mechanics, is not something you can predict with certainty. You can only assign probabilities. And before you check, the theory treats the atom as a mix of decayed and not decayed. So, what then is the state of the entire box? If you're strict about it, the atom is in a superposition. The detector is in a superposition. The mechanism is in a superposition. And the cat is in a superposition too, alive and dead. Not as a metaphor, not as a joke, as a direct consequence of applying the same quantum rules to the entire chain. Now, in real life, no one builds this box. And the moment you hear it, your mind tries to escape in the most human way possible by saying, "That's silly. Cats are either alive or dead, obviously." But that obviously is exactly what Schrödinger was attacking, because the quantum formalism doesn't contain a clear line that says superpositions are allowed here, but forbidden there. It doesn't politely stop at the edge of your intuition. It keeps going. So the cat becomes a pressure test, a stress fracture you can't ignore. And once it's on the table, three broad answers tend to appear, each one with a different kind of unease. One answer says, the act of observation causes collapse. The cat isn't truly alive and dead. The outcome becomes definite when someone looks. In this view, measurement is special. Observation draws a line through possibility and turns it into a single fact. But then the old question comes back with sharper teeth. What counts as looking? Is it a camera, a detector, a photon bouncing off the inside of the box, a human mind? If collapse needs a special kind of observer, then you're forced to explain why the universe should care. Another answer says there is no collapse. Both outcomes happen. When you open the box, you don't create a result. You discover which branch you're in. The cat lived in one branch and died in another, and reality quietly split into two consistent stories. This keeps the math clean, almost elegant, but the cost is emotional. It asks you to believe the universe constantly multiplies into unseen versions of itself, vast, silent copies that you never meet. And a third family of answers tries to rescue realism by adding something beneath the standard picture: hidden variables, pilot waves, objective collapse mechanisms, ideas where the cat is always truly alive or dead. And the uncertainty is about what we can know, not what exists. Those models can be compelling, but they tend to demand something in return: non-local connections, new physics, or rules that go beyond what ordinary quantum mechanics states. None of these options is free. That's the real lesson of the cat. It isn't there to be spooky for the sake of it. It's there to show you that the measurement problem isn't a small glitch in the margins. It's a fault line that runs from the tiniest quantum events, all the way up to the world of solid objects, memories, and living minds. And once you've felt that scale shift, once you've watched the weirdness climb the ladder into the everyday, another question starts to form naturally. If superposition can, in principle, spread upward, why doesn't it look like it does? Why does the world insist on giving us one outcome at a time? As if reality has already chosen a single story, long before we arrive to read it. If Schrödinger's cat feels like a nightmare, decoherence is the part of the story where the universe quietly explains why we don't live inside that nightmare. Because here's the uncomfortable truth: quantum superpositions don't only exist in equations, they are real features of quantum systems. The interference patterns are not a metaphor. The predictions are not poetry. When you isolate a system well enough, superposition shows up as measurable structure in the world. So, why doesn't your coffee cup behave like a quantum ghost, spreading into multiple possible positions at once? Why do tables, cats, and human brains look stubbornly classical? Decoherence is the reason the quantum weirdness usually doesn't survive long enough to be seen at human scale. To feel it, imagine what entanglement really does. It ties the description of one system to the description of another. In a quiet lab, you can entangle two photons and keep track of their shared state. But outside that controlled environment, there's a constant, unavoidable problem. Everything is touching everything, not in the dramatic sense, more like a whispering, incessant contact. Air molecules, thermal radiation, vibrations in the material, stray electromagnetic fields, tiny collisions, random phases, a million little nudges you never notice. Each nudge is an interaction, and each interaction is an entangling event. That means a system that starts out in a neat superposition doesn't stay neatly alone. Its quantum state begins leaking outward into the environment, like ink spreading through water. The system becomes correlated with countless degrees of freedom outside itself. And once that happens, something important changes. The superposition doesn't vanish, but it becomes effectively unreadable. In principle, the universe is still following the quantum rules. The combined system, your object plus the environment, is still described by one big quantum state. But in practice, the delicate phase relationships that allow interference get scrambled across the environment so quickly that no realistic observer can reverse it. So, the both-at-once behavior becomes inaccessible. This is why decoherence is often described as the mechanism that makes quantum systems look classical. Not by smashing superpositions into a single outcome, like a judge slamming a gavel, more by drowning the interference in an ocean of environmental information. It's also why, in the lab, the battle is always about isolation. If you want to see interference from something larger than an electron, you fight the world itself. Lower the temperature, reduce vibrations, remove air, shield fields, shorten the time. You try to keep the environment from learning anything about the system. Because the moment the environment learns which path a particle took, through a collision, a photon scattering, a tiny thermal interaction, the interference pattern fades. The world has, in effect, recorded the information. And when information is recorded, the different branches of the superposition stop talking to each other. They stop interfering. That is the eerie elegance of decoherence. It shows how classical reality can emerge from quantum laws without adding new physics. It makes it less mysterious why we don't see macroscopic superpositions every day. It gives you a reason that feels almost ordinary. But here's the catch. and this is where the comfort slips. Decoherence explains why the quantum maybe becomes practically invisible at large scales. It does not explain why you experience one outcome. It can tell you why the branches stop interfering, why the alternatives become dynamically isolated, why the world begins to behave as if it had chosen a definite story. But it doesn't answer the deepest question hiding underneath all of this. Why does your experience land on a single result at all? If the full quantum state includes multiple outcomes, each now separated, each no longer interfering, then what exactly turns many possible stories into the one story you live inside? Some interpretations say collapse is real and physical. Others say there is no collapse, only branching. Others say something deeper sits beneath the probabilities. Decoherence doesn't settle that debate. It simply sharpens it. It's like cleaning fog off a window and realizing the real mystery wasn't the fog. The real mystery is what's on the other side. So, decoherence gives us a powerful, almost satisfying explanation for the everyday world. Why cats aren't shimmering between life and death. Why tables don't blur into multiple places at once. Why your brain isn't a visible superposition of every thought you could have. But it also leaves a quiet, unresolved pressure in the background. If decoherence only explains why the alternatives stop interacting, then the question of selection, the question of the single outcome, hasn't gone away. It's just waiting for us, a little further down the thread. It's tempting to file all of this under philosophy, a beautiful argument, a strange thought experiment, a debate you can admire from a safe distance. But entanglement and measurement aren't museum pieces. They're tools now. We've built machines that only work because the universe really is this weird. Start with quantum cryptography, one of the cleanest proofs that the strangeness is physical. In ordinary encryption, a spy can copy a message without leaving a fingerprint. But in quantum key distribution, the key is carried by quantum states. If an eavesdropper tries to intercept and measure them, the act of measurement doesn't just reveal information. It changes the state. It creates errors that weren't there before. In other words, reality itself becomes the alarm system. You don't need perfect trust. You need the laws of physics. Then there's quantum teleportation, which sounds like science fiction until you learn what it actually means. No object vanishes and reappears. What gets transferred is the quantum state, the precise information that describes a system's condition. And it only works because of entanglement, plus a classical message sent the old-fashioned way. It's a beautiful hybrid. Quantum correlations do the heavy lifting, and ordinary communication closes the loop. Teleportation is not a metaphor. It's a laboratory procedure, and if you want the loudest, most practical confirmation, look at quantum computing. Still early, still difficult, but already real. The entire promise depends on treating entanglement as a resource you can engineer. You can't fake it with clever programming, because the advantage comes from manipulating superpositions and correlations that don't exist in classical physics. That's why these systems are so fragile, and why researchers obsess over error correction. The weirdness is powerful, but it's not forgiving. So, by this point, the question isn't whether quantum mechanics is just interpretation. The question is why the world lets us harness something so counterintuitive, and why measurement sits at the center of all of it, like a locked door. Because once you can use the weirdness, you can't dismiss it. You're not watching a philosophical debate anymore. You're watching engineers build reality into a machine, and discovering that reality has opinions. For a moment, let's hold two strange facts in the same hand. The first is entanglement, a situation where the universe refuses to let two things be fully described on their own. You can separate the particles by continents and oceans, and still the math and the experiments insist that what happens over there can't be told without referencing what happens over here. Not as a message, not as a signal, more like a single story being read from two different pages. The second fact is much closer to home and somehow even harder to explain. You are having an experience right now. Not just processing information, not just reacting. There is something it feels like to be you, reading, listening, noticing the texture of these words as they pass through your mind. And the unsettling thing is that modern science, for all its power, still doesn't know how to translate that inner light into the language of particles and fields. This is what philosophers call the hard problem of consciousness. Not the problem of intelligence. Brains clearly compute, predict, and control. Not the problem of behavior. Neurons fire, muscles move, words appear. The hard problem is why any of that comes with a first-person point of view. Why the universe, in at least one corner of itself, seems to have developed an interior. And here is why it belongs in the same conversation as measurement. Because measurement in quantum physics isn't just finding out. It's a boundary event, a place where a fog of possibilities, real, calculable possibilities, becomes one stubborn, irreversible outcome. Before measurement, the theory talks in amplitudes and superpositions. After measurement, the world hands you a single answer, a number, a click, a dot on a screen, something you can't unsee. That transformation is so clean in the equations and so mysterious in meaning. What is a measurement exactly? Is it any interaction? If so, why don't we see superpositions all around us all the time? Is it the environment watching through endless tiny entanglements? If so, why does that feel like it explains the loss of interference, but not the appearance of one specific result? Or is measurement something more special, a moment where information becomes fact? Notice how the language starts to drift. Fact, information, observation, knowledge. Words that sound physical on the surface, but carry a faint shadow of mind. And that's the bridge we're standing on. Because consciousness has its own version of the same puzzle, we can map the brain in exquisite detail. We can watch neural networks light up when you recognize a face, feel fear, recall a memory, or drift into sleep. We can stimulate regions and change perception. We can measure correlations between brain states and reported experiences. That's the easy problem, the science of functions, mechanisms, and patterns. But then the harder question returns patiently, like a tide. Why is there anything it is like to be the system doing the measuring? Why isn't the brain a perfect zombie machine? Competent, adaptive, eloquent, and completely dark inside. If you're listening to this while you're sleepy, you might feel the irony even more sharply. As your thoughts slow down, as the world softens at the edges, you don't become less real. Your inner world becomes more obvious, more undeniable. A private space where the universe seems to be present to itself. And this is where the similarity becomes almost uncomfortable. In quantum mechanics, the story seems to demand a line between possibility and actuality. In consciousness, the story seems to demand a line between description and experience. One line turns a wave of could be into a single is. The other line turns a physical process into a live moment. Now, to be clear, this doesn't prove that minds collapse wave functions. It doesn't prove that quantum theory needs consciousness. Many physicists believe the universe doesn't care whether anyone is watching. That measurement is just interaction, and observers are just complicated pieces of matter. That's a perfectly respectable view. But even in that calmer interpretation, the rhyme remains. Quantum theory tells us the universe is not a simple catalog of properties sitting there fully formed, waiting to be read. Something about having a value depends on context, on how a question is asked, on what is measured, on what is excluded. And consciousness tells us something equally strange. You can describe every ingredient of a brain from the outside and still be missing the central ingredient from the inside. So maybe they're unrelated, two mysteries that simply happen to share a word like observation. Or maybe, in a deeper way, they are two sides of the same ancient problem, how reality becomes definite and how reality becomes felt. Either way, this is the doorway. We've walked from entangled particles to engineered devices, and now we're standing at the edge where physics starts to touch the outline of mind. And once you notice that outline, it's hard to stop looking. There's a moment in this story where the conversation almost can't help drifting toward the most provocative question of all. Not is entanglement real, because it is. Not is measurement strange, because it remains one of the deepest open knots in the foundations. But something quieter and more unsettling. What if the act of becoming definite is not completely separate from the act of becoming aware? That question has tempted scientists and philosophers for decades, and most of the time, it leads to vague poetry or sloppy claims. But there is one proposal that tries, at least, to be specific. A proposal with names, mechanisms, and a clear target. It's usually called Orch-OR, short for Orchestrated Objective Reduction, and it sits at the crossroads of two bold ideas. The first comes from Roger Penrose, the suspicion that collapse might be a real physical event, not just a bookkeeping trick in our equations. In many standard interpretations, wave function collapse is tied to measurement, an update to knowledge, or an effective description. Penrose didn't like that. He proposed that superpositions might have a natural limit, especially when gravity enters the picture. Why gravity? Because in general relativity, gravity isn't a force sitting on top of space. It is the geometry of space-time. If a quantum system is in a superposition of two different locations, or two different mass distributions, then, in a sense, it may be in a superposition of two different space-time geometries. Penrose argued that this kind of split space-time might be unstable, that nature might resolve it on its own after a certain threshold is reached. Not because an observer looked, because reality, at some scale, refuses to remain smeared between incompatible structures. That self-triggered collapse is what he called objective reduction, OR. The second idea comes from Stuart Hameroff, who looked toward the brain, not at neurons firing in bulk, but at structures inside neurons called microtubules. Microtubules are part of the cell's internal scaffolding, and in Orch-OR, they're imagined as a kind of organized arena where quantum effects could, in principle, be protected, coordinated, and orchestrated into meaningful patterns. Put those together, and you get the Orch-OR claim in its strongest form. Conscious moments might correspond to discrete physical events, objective collapses, occurring within orchestrated quantum states in the brain. Not consciousness causing collapse, but collapse being part of what consciousness is. It's an audacious thought. And that audacity is exactly why it keeps resurfacing in viral conversations about quantum mechanics and mind. Because it offers a satisfying shape. It says, the mystery of measurement and the mystery of experience might be related, not by metaphor, but by mechanism. And yet, almost immediately, the skepticism arrives, calm, patient, and heavy with practical concerns. The first concern is the most famous one. The brain is warm, wet, noisy, and busy. Quantum states, especially delicate superpositions, are notoriously vulnerable to decoherence. In many lab settings, you need extreme isolation, ultra-cold temperatures, and careful shielding to preserve quantum coherence long enough to do anything interesting with it. The brain is not a vacuum chamber. It is a biological storm of thermal motion and chemical interaction. So the skeptical question becomes simple and sharp. Even if microtubules exist, can they truly sustain quantum coherence at timescales that matter for cognition? Because cognition runs on milliseconds. Neural spiking, perception, attention, these are not trillionths of a second. Many critics argue that any fragile quantum coherence in a warm biological environment would collapse far too quickly to play the role Orch-OR assigns it. And even if the theory is adjusted, suggesting special protections or exotic coherence mechanisms, the skeptics raise a second concern. Where is the clean evidence? A strong scientific claim needs anchor points, experiments that produce distinct predictions, measurements that would clearly support the hypothesis over simpler alternatives. Orch-OR has suggestive arguments and ongoing debate, but it doesn't yet have the kind of decisive laboratory signature that forces the world to update its textbooks. It lives in that difficult territory where an idea is not obviously impossible, but also not yet firmly compelled by data. Then comes the deeper skepticism, the one that doesn't even depend on decoherence timescales. It goes like this. Let's imagine, generously, that some quantum process in the brain is real, meaningful, even essential. So what? Why would quantum computation, or objective collapse, or an entanglement feel like anything? This is the problem, the hard problem people won't let you avoid. You can add as much physics as you want, more complexity, more elegance, more mystery. And the core question remains, how does a physical process acquire an inner point of view? A skeptic might say, quantum mechanics is weird, yes, but weird is not the same thing as conscious. Quantum entanglement doesn't automatically imply experience. Superposition doesn't automatically imply awareness. Non-local correlations do not automatically imply a self. And yet, Orch-OR persists, not because it's proven, but because it gives a concrete answer to something most theories refuse to touch. It tries to locate a moment where the world changes from possibility to actuality, and then dares to suggest that this same pivot might be the pivot of experience, moment by moment, frame by frame, like a quiet internal cinema. In that framing, consciousness isn't an endless stream, but a sequence of discrete events stitched into continuity by memory, attention, and narrative. A series of tiny now points, each one a selection from a cloud of alternatives. Again, intriguing, unproven, but it has a shape you can hold. So, where does that leave us if we're being honest and careful? It leaves us with a balanced posture, the only posture that deserves to survive into the morning. Orch-OR is not mainstream consensus. Many physicists and neuroscientists remain unconvinced, and the objections are serious. But it also isn't mere fantasy. It is a serious attempt, however controversial, to connect two mysteries with a single hinge. And that hinge matters, even if it turns out to be the wrong one. Because the moment you ask whether consciousness could be woven into the same fabric as measurement, you step into a larger landscape, one where mind is not treated as an afterthought, but as something that must be accounted for in our map of reality. Some people walk that landscape by saying consciousness might be a fundamental feature of the universe, present in simpler forms everywhere. Others try to measure it, to quantify it, to turn it into something that can be compared across systems. And once you allow those possibilities into the room, the conversation changes shape again. If Orch-OR is the bold attempt to weld consciousness to a specific quantum mechanism, this next zone is different. It doesn't try to hide inside microtubules or propose a secret quantum engine in the brain. Instead, it steps back and asks something even more unsettling. What if consciousness isn't an exotic late feature of the universe, but a faint basic ingredient that was there all along? That family of ideas is usually grouped under a single word that sounds almost too simple for how heavy it is. Panpsychism. The core intuition is disarmingly plain. Matter behaves in lawful ways. Brains are made of matter, brains produce experience. So, maybe experience isn't something that suddenly appears out of nowhere at a certain complexity threshold. Maybe what appears in brains is not the birth of consciousness, but the organization of something already present in a quieter form. Not thoughts, not feelings, not a little person inside an atom. More like a primitive something it is like at the smallest level, so minimal that it doesn't resemble what we mean by mind, but still counts as a sliver of interiority. This is one reason the idea keeps returning in serious discussions. It tries to avoid the feeling that consciousness is a magical exception. It aims to close the gap between the physical description of the world and the undeniable fact that experience exists. But panpsychism doesn't solve the mystery for free. It trades one hard question for another that may be even harder to picture. Because if tiny pieces of matter have tiny pieces of proto-experience, how do those pieces combine into one unified stream? This is the famous combination problem. You know your consciousness as a single field, one scene at a time, one you at the center of it. Your experience is not a committee meeting of trillions of micro-experiences voting on what you should feel, and yet your brain is made of countless interacting parts. So panpsychism offers a haunting possibility, then immediately gets cornered by an even more haunting demand. Show me how many becomes one. And that's where a second framework often enters the conversation, one that tries to sound less like metaphysics and more like a measurement program. Integrated Information Theory, or IIT. IIT begins from a different starting point. Instead of guessing where consciousness comes from, it asks what consciousness is like from the inside, and then tries to translate those features into requirements for a physical system. Conscious experience feels integrated. It arrives as a unified whole, and it feels informative. Each moment is a particular way the world could be, and not a million other ways. So IIT proposes, in rough terms, that a system is conscious to the degree that it generates integrated information that cannot be reduced to independent parts without losing something essential. It's an attempt to put a number on a slippery concept, often represented by a quantity called phi, meant to capture how deeply a system's causal structure hangs together as a single entity. This is why IIT is so attractive in the same way competitor-style videos love. It feels like philosophy wearing a lab coat. It offers a bridge between talk about experience and talk about mechanisms, as if you might someday evaluate consciousness the way you evaluate a circuit. And to be fair, IIT has inspired real research conversations about anesthesia, sleep, disorders of consciousness, and how we might distinguish wakeful awareness from something that only looks awake from the outside. But here too, the skepticism arrives, quiet but firm. First, there are disputes about whether phi can be defined and computed in a clean way for real brains and real networks. Even when you can compute something, critics argue that the result might not track what we intuitively mean by consciousness. Second, IIT has faced a deeper kind of criticism, that it may assign consciousness to systems in ways that feel absurd. Depending on the version and assumptions, certain simple arrangements might score unexpectedly high, while systems we'd assume are conscious might not fit neatly. The theory's supporters see this as a feature, proof that our intuitions are unreliable. Critics see it as a warning sign, proof the formalism has slipped away from the phenomenon. And then there's the unavoidable philosophical sting. Even if you could calculate the perfect number, why should a certain causal structure be experience? Why should integration, no matter how elegant, light up an inner world? So in this stretch of the journey, you feel the tone shift, not from science to fantasy, from science to the edge of what science can comfortably certify. Panpsychism offers a way to make consciousness feel less like a cosmic accident, but it struggles to explain unity. IIT offers a way to make consciousness feel measurable, but it struggles to convince everyone that the measure captures the thing itself. And still, people return to both ideas for the same reason, because they refuse to treat consciousness as a footnote. They treat it as something that must be accounted for, either as a basic feature of reality, or as a property that emerges when information becomes inseparable from itself. And once you entertain either possibility, even for a minute, the story takes on a wider horizon. Because the next thought is almost inevitable. If consciousness is fundamental, or if it can be defined in a way that applies beyond brains, then it becomes tempting to ask whether the universe itself might carry some faint, global interiority, beautiful to imagine, difficult to test, and dangerously easy to overstate. And that's the point where the story becomes almost too easy to misread. Once you hear words like non-local and observer and measurement, the imagination wants to sprint ahead toward the idea that the universe must be secretly alive, secretly aware, secretly thinking. And it's a beautiful thought. The kind of thought that feels like it belongs under a sky full of stars. But beauty is not the same thing as evidence. What we can say, carefully, honestly, is simpler and in a strange way, even more profound. Entanglement is real, not metaphorically, not spiritually. Real in the way that experiments can punish you for getting the math wrong. Measurement is still mysterious. Not because scientists are lazy, but because the universe refuses to tell us cleanly what a fact is before it becomes a fact. And consciousness is undeniable. You can doubt almost anything, except the fact that you are here, having an experience of doubting. So When people talk about cosmic consciousness, it often comes from a quiet discomfort. How can a universe described in the third-person equations produce a first-person point of view? Some take the leap and say, maybe the universe doesn't produce consciousness, maybe it contains it. Maybe minds are not a glitch in matter, but a natural way matter can be arranged. Maybe what you call you is one of the universe's ways of looking back at itself, not as poetry, but as a possibility we don't yet know how to test. And that last part matters, because in science, the most disciplined phrase is sometimes the gentlest one. We don't know. We don't know whether consciousness is a deep principle, or an emergent trick, or something in between. We don't know whether measurement needs an observer, or whether observer is just shorthand for an interaction that becomes irreversible. We don't know whether the link between physics and mind is a bridge we'll build, or a rhyme we'll simply notice. But tonight, you followed the thread anyway. From a pair of particles split across the earth, to a question that sits quietly behind your own eyes. And even if the connection remains unknown, the feeling it leaves can be oddly calming, because it reminds you that reality is bigger than your worries, deeper than your deadlines, older than every fear you've ever carried. If you enjoyed drifting through this with me, you can tap like, subscribe, and leave a comment. Tell me where you're listening from tonight. I always love seeing how far this little quiet corner of the internet reaches. And now, you don't have to solve anything. You can let the questions stay open, let your thoughts loosen their grip, let the day fade down to a softer volume. Thank you for spending this hour with the Quantum Slumber. May your mind feel lighter, your breathing slower, and your sleep come gently, like a wave that doesn't ask permission. Good night.